So this is joint work with Yuanzi Chen from Duke University. And kind of like the topic of this talk is more or less like this talk will basically do the following. So we'll look at the framework that basically the first two talks talked about, spectral independence, entropic independence, and its various extensions. And we'll basically find a unified point of view for this framework with another analytic technique called stochastic localization that was used mainly, both techniques kind of were used to prove spectral gaps, concentration bounds, mixing times, etc. The second techniques was used mainly in the continuous setting. Also, it had applications in the discrete setting. The first technique was mostly, or I think only, in the discrete setting, and we're going to find, I'm going to introduce a unified point of view that works in both settings, kind of connects the paradigms from both techniques. And one of the main features is going to be that, so the first technique was, is heavily based on the theory and ideas from high dimensional expanders. And our framework is just going to completely get rid of that for the good and for the bad. And instead, we're going to use martingale techniques to show most of the things that, among other things, the things you saw in the first two talks. Okay, so let's dive into it. So just a quick recap on basically the background. Most of it you saw before. So our goal in this talk is going to be the following. You have some given probability measure, or we call it nu, on some space omega, which can be either discrete or continuous. In this talk, it'll be mainly either Rn or the discrete hypercube -1,1. Even though the principles of this framework work beyond these two settings, we'll talk mainly about them. And what we want to do is we want to sample from this measure, and we assume that we have access to, well, not exactly the density of the measure at any point, but the density up to some multiplicative constant. So we might not know the normalizing constant, but we know some, up to this, we can query the density. And a common way to sample from measures like this is by using a Markov chain. So we saw a few examples in the last two talks, but in general, what's a Markov chain? So we want to find some transition kernel, P x goes to y, that for every pair of points in my space x and y, the transition kernel is just the probability that the step of the random walk starting at x will be at y in the next step. So just the transition from x to y. And we assume that the Markov chain has nu as its stationary measure, meaning that if I started my first step randomly distributed from the measure nu, and then I do one step of the Markov chain, I assume that after this step, I'm still distributed as nu. And if you want to write it, this is a simple way to write it. And if in a formula, we take the measure nu, we plug it into this transpose of the transition kernel, and we get the measure nu back again. Okay, and usually what we'll want is to say something about, I don't need to do many steps until I actually reach the stationary measure. So this concept we had in the previous two talks already. Some measures to keep in mind, just an examples for this talk. So the first family of measures is log concave measures on Rn. So suppose I have some convex function on Rn, V, and then I take just the measure whose density is e to the minus V of x. Okay, so One example is if V is just the norm of X squared, you get the Gaussian measure. For any convex set, you can take the function V, which is 0 on the convex set and infinity outside, and you'll get just the uniform measure on the convex set. And there are many measures of interest that, you know, have this form. The second family of measures is what we call graphical Ising measures. So what is that? Suppose we have some graph G. So say those are its vertices, and it also has some edges. And what we think about is some spin system of G. So the distribution is going to be over assignments to plus or minus 1 to each one of the vertices. And what's the density of this distribution? It's just going to look like the uniform distribution, but we reweigh the uniform distribution by this formula, which is just taking the exponent on, you can think of this sum as the total agreement between adjacent spins in the graph. So whenever I have two vertices where the spins agree, maybe this is +1 and also this is +1, this edge will be counted as a positive, you know, summand in this big sum. So we kind of want to enforce agreement between neighboring edges. Well, this is in the case that this beta, called the inverse temperature, is positive. Sometimes beta can be negative, and then we kind of want to enforce disagreement. Okay, so we have this graph, and the structure of the graph gives us a distribution on the discrete hypercube, you know, basically whose coordinates are parameterized by the vertices of the graph. And the third example we'll have in mind is the hardcore model, which, you know, Zonchen talked about quite a lot in his talk. So suppose, again, we have a graph, and we want to sample an independent set basically almost uniformly, but we reweigh by some parameter lambda called the fugacity to the power of the size of the independent set. So usually, you know, if lambda is more than 1, we kind of want to put our balance into as big as possible independent sets. In our settings, it's usually going to be less than 1, which we kind of, you know, want to incentivize that independent set to be like not too big. But okay, these are going to be our examples. Know that like this is just a bunch of measures on Rn, and the second one and the second and third are just a family of measures on the discrete hypercube. Okay, let me go on. I'm going quite fast again over the background. So please, just because we already went over this in the previous two talks, but please stop me if you have any questions. Okay, so what's a natural family of Markov chains to consider? It's usually natural to consider Markov chains that only do local updates. The reason is that if we don't do local updates, it's just going to be pretty hard to compute even one step of the Markov chain. So what do we mean by local updates? Suppose we do a random walk on the discrete hypercube. So this is the two-dimensional discrete hypercube, and suppose that at some time step, our random walker is over here. What we're going to do is at every step, we're just going to update one coordinate of our random walker. So in the most canonical chain, perhaps called Glauber dynamics, what we're going to do is we're going to pick uniformly which coordinate we're going to update among the n coordinates. So perhaps we decided that we're going to update this vertical coordinate. Once we made this decision, then, you know, the next step is basically going to, it's going to keep all the other coordinates fixed, and it's just going to update this particular coordinate. meaning that the next step is just going to land either at this point or at this point. And how are we going to choose which point we land it? Well, we're just going to do it proportional to the measure proportional to the density at each of these 2 points. So, you know, the probability to land at point Y, we only have these 2 points here. They're, let's call them X and Y. And the probability to land at Y is just the measure of Y over the measure of these 2 points together. So this is Glauber dynamics. I guess Zon Chen gave a slightly different kind of explanation for what it is, but if you think about it for a second, it's just the same thing. I mean, you can just think of like a spin system on a graph. Every time you just update one spin and you condition on the, you know, on what all the other spins are at that step. Okay, it's pretty easy to see from this formula that the chain is reversible. So nu of X. So what does reversible mean? It basically means that the flow of probability between each 2 vertices in both directions is the same. So this, so the measure of this vertex, the measure of this vertex times how much flow I have from here to here is equal to the measure of this vertex times how much flow I have from here to here, which, you know, basically immediately tells me that nu will be the stationary measure. And this formula is just to tell you that Glauber dynamics is just one example of a local random walk. If we, so Glauber dynamics is essentially just the usual random walk with respect to the uniform measure on the discrete hypercube times this change of measure that makes nu the stationary measure instead of the uniform one. You can do just the same thing, for example, on Rn by taking a random walk with Gaussian steps, which, you know, if the space is not compact, so there's no reason to talk about the uniform measure. But if you think of a torus, for example, you can think of a random walk with these steps and do exactly this same change of measure, and you will get, you know, a reversible Markov chain with nu as its stationary measure. So those are local updates to the, those are 2 examples of Markov chains that only do local updates. Here, the locality is in the sense of updating one coordinate, and here the locality is in the sense of, you know, if you have a small Gaussian, it only updates locally. Okay, and what do we want to say about these chains? So, you know, usually we want to say something like, I start from some point and I don't need to do many steps of the random walk until I mix in, say, total variation distance. So this notion of mixing time is exactly that. I start from an arbitrary point. How many steps do I need to do until the total variation distance is at most epsilon? So again, we already seen this in Zon-Chen's talk. And somehow the most common paradigm that is used to prove upper bounds on those mixing times are via functional inequalities. So maybe the most basic functional inequality relevant here is just a spectral gap inequality. So we just look at this transition kernel P as an operator, and we look at the spectral gap of this operator. So this operator has one eigenvalue equal to 1, and we just check what's the next eigenvalue. So all the others are less than 1, and we just want the distance between the second biggest and the biggest eigenvalue. That's called the spectral gap, and it's quite standard to show that the mixing time is bounded by something that looks like the inverse spectral gap. and we can do just the same thing. So spectral gap is a variance-like quantity. There is an analogous entropy-like quantity, which basically says by how much the relative entropy to the background measure decays when I do one step of the random walk. And this is called the modified log Sobolev constant. And it also gives a bound on the mixing time. So I guess this, in Nima's talk, this was called rho spectral, and this was called rho entropy. Those are just exactly the same things. Okay, and so both give bounds on the mixing times, and this gives a better bound. This somehow has the potential to give an optimal bound in many cases. This usually loses this factor n here. Okay. Now, let me try to talk a bit about the spectral independence framework, but from a slightly different point of view that was from what was presented in the previous two talks. And for that, I want to begin with some obvious obstacle that we have to mixing. So some condition under which we know that the Markov chain is not going to have fast mixing and not even polynomial mixing. And for that, I guess the most basic example to consider is what's called the Curie-Weiss model. And what is that? That's a graphical Ising model for the complete graph. So it's a distribution on the discrete hypercube. Let me draw like this, the discrete hypercube, where this direction is the, so I kind of want to draw it so that this direction is the all ones direction. It counts how many positive spins I have. And what I do is I take the uniform measure and I reweigh it by the total number of agreements between different spins, the exp of that. So it's kind of clear that this measure will only depend on the sum of spins, right? Just by symmetry. So the density will be constant on each one of these slices here that we consider. And on each slice, what will be the density? Well, it's just going to be whatever I had for the uniform measure. So I'll just have basically the marginal of the uniform measure onto the all ones direction. So, you know, here it's going to be quite small, and here it's going to be bigger, and here it's going to be the biggest, and here it's going to be small again. But I'm going to do a reweighing by e to the positive, this thing, which is, you know, this is nothing but the sum of xi squared, right? So I'm actually doing a reweighing where the density here and here is multiplied by a bigger thing than what it's multiplied by at the center. Okay, so somehow this incentivizes the spins to align with each other, whereas the uniform measure incentivizes the spin. I mean, there's no incentive, but most of the entropy is where the spins just average to something close to zero. And there is a competition between those two things. And what we get is that if this beta is large enough, then this term beats the entropic term coming from the uniform measure. And what we'll see is that the marginal basically looks like something like this function. So it's actually going to be small at the center of the hypercube, and it's going to be bigger when we go to the sides. And then basically what happens is the following thing. I guess it's not so hard to imagine that if the measure is essentially supported here and here, and I do a Markov chain that only does local updates, so I only kind of move locally, then it's very hard to move from this chunk to this chunk. It's kind of very hard to cross this valley in the center where you almost have no probability. Okay, so if I take the marginal of the Glauber dynamics onto the all ones direction, it's going to look more or less like, well, kind of like a random walk that has drift that's pushing it back from the center. And it's going to be very hard to cross the center. And actually, if beta is bigger than some constant, it's going to take exponential time to cross the center. And it'll have a very bad mixing time. So this is called the low temperature regime. And it's easy to see that in this example, some property that we have of this measure is, if we look at the covariance matrix of this measure, then in the all ones direction, it's actually pretty huge. The variance is really huge because it's either this sum is going to be something like order n, or it's going to be order minus n, right? So the covariance matrix in this direction is much bigger than 1. Okay, this is kind of an important example because I feel like it's the most natural way to lead to what comes next, which is this spectral independence framework, at least the way I see it. And you know, the question that I don't know if this is the case, but I guess the question that Nima, Kuikui, and Cheyenne might have asked themselves is, could it be that large covariance matrices are essentially the only obstacles to mixing? So it's clearly an obstacle to mixing, but is it the only one? And what they say in their framework is, the answer is almost yes. So no, not exactly yes. It's not enough to have a small covariance matrix. But if we have a small covariance matrix under all pinnings, and what do I mean by pinnings? Pinnings is just, I take some vector that has -1s, stars, and 1s, and I basically, you know, I condition the measure on the coordinates which have -1 and +1 to be whatever value this is, and I leave some of them free. So I pin some of the coordinates into some prescribed values. And suppose that for all pinnings I have small covariance matrices, then I have a spectral gap. So what they have is not exactly the covariance matrix, it's what you saw in the previous two talks called the influence matrix, but it's actually pretty hard to see, easy to see, sorry, that there is an easy connection between the two notions of influence matrix and covariance matrix. So actually, you can just think of this as covariance matrix. And what they show is that the spectral gap is lower bounded by this telescopic sum that has here the operator norms of the covariance or influence matrices for all pinnings. And in particular, if all of these are bounded by, if all of these are O of 1, we get a polynomial spectral gap, which implies polynomial mixing time. So this is kind of like the general, or maybe the first principle of this framework that was extended quite a lot. What Nima talked about is kind of a condition where I have something not for all pinnings, but for all external fields. External fields are, you know, pinnings can be seen as a special case of pinnings. And then you get something even better. Okay, so this is their framework. And we're going to kind of connect this framework to something that comes from a different area, which is, it was inspired by the Cannon-Lovász-Simonovitz conjecture, which is also a conjecture about a spectral gap of some transition kernel. I'm not going to tell you exactly what this transition kernel is, but it's also a local update Markov chain, this time on measures on Rn, and it's an infinitesimal update. So this transition kernel has to do with the Langevin dynamics, and the KLS conjecture just says that for low concave measures, this is at least a constant, and one way to approach these kinds of inequalities is by this stochastic localization technique, whose kind of the main paradigm in stochastic localization was the following thing. So we want to prove a lower bound on the spectral gap for some measure. And what we do is we take this measure and we associate it with some stochastic process that is measure valued. So a process of measures which kind of interpolates between the original measure at time 0 and a Dirac measure at time 1. And somehow the lower bound on the spectral gap is like the main paradigm of the framework is that it's reduced to upper bounds on the covariance matrix of these measures, the measures that we get during this process. So, you know, this looks a lot like what we saw before. We need an upper bound on the covariance matrices of a family of measures, which implies some spectral gap on the original measure. And in the time I have left, let me try to kind of tell you how one can try to connect between the two things, which, you know, at least from the formulation, from a high level, are seemingly, you know, share some common principles. So somehow the main construction in our framework is a localization process. What's a localization process? So we fix, again, a state space omega and the measure, a probability measure on omega. And a localization process is a stochastic process, nu t, such that for every time t, nu t is a probability measure. So it's a random flow of probability measures that has the following additional properties. So first of all, for every set A, if I look at nu t of A, this is now a scalar valued stochastic process. I want this to be a martingale. And the second property, or the third property, is that for every A, at time infinity, when the process is kind of done, the measure of A is either 0 or 1, meaning that, you know, this measure has localized to somewhere. It cannot be supported on more than one atom, but at time infinity, it kind of completely localized to a point. So this is kind of an interpolation, a random interpolation between the measure nu and a Dirac delta measure that does this interpolation happens in a martingale way, okay? And what's a localization scheme? It's basically something that takes some given measure and assigns to it a localization process that such that at time 0, I start with this given measure. So it's just a way to interpolate between the measure and a Dirac delta function in a random way. Some like examples of localization schemes. So maybe the most basic example is if you have a measure on the hypercube. I guess almost all of you saw the martingale revealment process. So it's just the following process. I take some uniform order of the coordinate, and I generate a discrete sequence of measures by, at every iteration, I reveal one coordinate of where I am actually going to sample according to the order that I generated. And I set nu I to be just the law of my final point conditioned on the coordinates that I already revealed. Okay, so say I have a measure on the two-dimensional thing. So maybe first I reveal the first coordinate. So I'm going to be either here or here. So suppose I chose this side, then I just take the measure conditioned on these 2 points. Sorry, I don't understand what's going on. So suppose I revealed the first coordinate and I chose to be here. So I get the measure conditioned on these 2 points. And then I reveal the second coordinate and I choose to be here. And I end up, you know, with a Dirac delta on this point. and the intermediate things are just the condition measures. The second one is seemingly unrelated, but we'll see in a few minutes that it's actually related, is the Gaussian channel localization. This works for any measure on Rn, or also on the discrete hypercube if we think about it as embedded in Rn. And nu t will be defined like this. We take a point sampled from our measure and take a Brownian motion on Rn, and then nu t will be the law of the endpoint conditioned on this noisy version of the endpoint. So we take t times this endpoint, which we don't know, just think about it. Someone chose this point x. He's not telling us what it is. He's just telling us noisy versions with kind of like decreasing noise. So as t advances, you have more of x, then you have like this is like bt increases like root t, and this increases like t. So the ratio actually goes more and more in favor of x. So as t increases, we have more and more information of where we're going to be, and we look at this sequence of conditional measures. It's not hard to see that at time infinity, you already know what x is.
Ronen, okay, so
yes.
maybe my question was, I mean, is there a physical interpretation of what is going on in the second case?
I mean, yeah, that's like physical. I mean, it's you know, it's just a Gaussian noisy channel in a sense. But the point is that it's usually kind of going backwards from the usual kind of Gaussian diffusion, where the usual heat equation somehow says, you know, you do this, you convolve with bigger and bigger Gaussians, and then you know less and less about your measure, and this kind of goes backwards in time. But you know, it's very related to the heat equation, if you want. I mean, that's a partial answer already to your question.
So is it like the inverse of the heat equation, where you, in some sense, the dynamics?
In a vague sense, not really, because I mean, yeah, I guess you could take a point of view where.
So I mean, let me ask this question: I mean, if I take the heat equation at some point, starting at some initial point, and run it and let it diffuse, and then I look at the time reverse version of this, would that be a localization scheme?
No, it's not a martingale.
Okay, so I'm missing some subtleties here then.
It's kind of like, it's more like, you know, at any point in time, all of these localization schemes are kind of like, at any point in time, I give you a noisy version, not of the measure, but of the final point. And I give you less and less noise as time progresses. Okay?
Okay, yeah, let you proceed, yeah. Thanks.
Cool. Okay, now there turns out to be a very natural way to associate a Markov chain with the localization scheme. So, you know, we add just a localization scheme which assigns to every measure a localization process. And it turns out that for every such assignment, there is actually a dynamics associated with it. And the way to define the dynamics is actually pretty simple. So it's defined via this formula. So let's try to understand what this formula says exactly. So we had the background measure, and we have this point x, where, you know, we want to understand what a random walk step from x is going to do. What's the distribution for the next point? So you could say, run the localization up to some time tau, some fixed time, and then just choose the next point from the you know, measure that you got at time tau. But this is kind of dumb because it does not depend on x at all. This is just going to give you the stationary measure after one step. So a natural thing to do is to take this localization process and reweigh the probabilities by this ratio. So we kind of want to say, the bigger the probability we have to land at the point X, the bigger the chances are that this is the actual path I sampled from my localization process. So in the case of coordinate by coordinate localization, this just means the following. Suppose I'm right here at the point X. I'm going to sample the coordinate by coordinate localization, say until up to time n-1. At this time, I only have 2 points left. But when I do this reweighing, I effectively condition on my localized measure to contain the point X. So my localized measure can either be this or this. And then when I choose Y from this localized measure, it's going to be exactly what the Glauber dynamics does. So this is just, you know, it looks like abstract nonsense, but it's actually useful when we want to analyze what happens with Glauber dynamics. And it turns out that for the Gaussian channel localization, you get exactly something called the restricted Gaussian dynamics that was introduced just 2 years ago by Lishan and Chan. And there are many other natural localization schemes give rise to natural chains like the hit and run walk, the down up walk, field dynamics, and yeah, several other things. And the nice thing about it is that it turns out that if you want to, so recall that we wanted to prove functional inequalities for a measure, and it turns out that those quantities related to the functional inequalities, the spectral gap and the modified log Sobolev constant, have very natural interpretations in the in the language of these localization schemes. So if we want to say something about the spectral gap, it's just a few lines calculation to show that it's equivalent to the following thing. And what's the following thing? It says it says take a test function phi on your space. So you have the space omega, and you choose some test function phi here. And phi has some variance with respect to nu. And then you run this localization process up to this time tau that we used to build the Markov chain. So when we run the process, we start from the initial measure, and the initial measure localizes in space. So maybe at time tau, we have some measure that is localized right here. And what we want to say is that even if we localize, even for the localized measure, the variance of this test function phi on this smaller measure is still a non-negligible fraction of the variance on the entire space. So we want to say that even though we localized on a small portion of the space, we still attain a little bit of the variance. And if we want a modified log Sobolev constant, we need to do exactly the same thing with entropy. We want to say that after localizing, we attain some entropy. Now, given that we want to say something about the ratio of variances between time 1 and some other time tau, and we have a process parameterized by time, it's natural to just check how quickly the variance decreases with respect to the process. So it's natural to take a test function phi, run this process, and see how the variance decreases as we localize on space. So in the end, we want to say something about the ratio between the variances at time 0 and some prescribed time. We can always write this as a telescopic product. And if we know that the decrement is not so big in one step, we will basically we'll be able to say via the telescopic product that you don't decrease after many steps also. Okay. And this telescopic product is the reason that you remember you had a product in the spectral independence result. This is kind of going to be the same thing. Okay, so so for this we have this notion of approximate conservation of variance that says that variance does not decrease too much. And I guess I started a few minutes late, right? Can I take a few more minutes? I have just like
oh yeah, go ahead.
Okay,
I
great.
also interrupted you for a couple of minutes. So.
Thanks. Okay, so it turns out that there is a family of localization processes for which we get very tractable expressions for how quickly those variances contract. And those localization processes, we call them linear tilt localization. They're just defined by, they're defined iteratively. So suppose you had the measure at time t. How do you obtain the measure at time t plus 1? Well, you just take the measure at time t and tilt it linearly. You take the density and at every iteration, you multiply it by a linear function where the direction of the gradient of the linear function is chosen randomly. And it's crucial that the expected gradient will be 0. This will make sure that this thing is a martingale difference, which means the measures will be a martingale. And you multiply by a linear function that's equal to 1 at the center of mass. If x is equal to the center of mass, this will just be 0, and you multiply by 1 at the center of mass. When you multiply a measure by a density by something equal to 1 at the center of mass, you do not change the total measure. So if you had a probability measure, you'll also have a probability measure afterwards. So this is kind of, this term accounts for the degree of freedom for the condition that you have to remain a probability measure. This thing accounts for the fact that you have a martingale, but otherwise you can choose this ZT as you want. And this will give rise to a family of localization schemes. And it's pretty easy to see that the coordinate by coordinate localization can easily be described this way. In order to condition one coordinate to be plus or minus 1, this is the same thing as multiplying by a linear function that's equal to 0 on one side of the discrete cube, is constant on the other side, and is equal to 1 at the center of mass. Okay, but there are many other localization schemes like this, and somehow one that has been very useful is to consider kind of exactly the same thing when we multiply by linear functions, but instead of doing it in discrete time steps, we do it infinitesimally. So somehow at every infinitesimal time step dt, we multiply by the increment of a Brownian motion, and this gives rise to a continuous system of stochastic differential equations, and you get something that, well, seems pretty canonical. And if you have this choice of variance of Brownian motion at each time t, and if you take this to be the identity, it turns out that the Markov chain associated with this localization process is exactly this restricted Gaussian dynamics that was recently introduced. I don't have time to touch that. I guess I only have like, I don't know, 3 more minutes, or just to get to one punchline. Yeah, okay, great. So good. So for this family of measures, we want to analyze how quickly the variance of some test function decays along the process. And And in the next basically slide and a half, I'm just going to tell you how this all connects to covariance matrices, which was kind of the whole point of the framework. You have some a priori bounds on covariance matrices, and you want to say something about spectral gap. So we want to go from covariance structure to variance decay. And with this framework, it's actually very easy to see how it happens, because if you look, so we fix a test function phi, and we want to understand the change of variance of phi with respect to the measure nu t as t increases. And by the law of total variance, this just corresponds to the variance, to the local variance of this quantity. This quantity is just the martingale, which is, what's the expectation. This is basically, it's already written here, the expectation of the test function with respect to the measure along the localization process. And the point is that when you try to understand how this integral changes, you just use the formula that defines the localization process. So you know how the measure changes with time, and you know that the change with respect to time has to do with this x coming out. So this basically says that when I differentiate this quantity with respect to time, I have this moment generating property of the process, that the differential of quantities with respect to time along the process correspond to spatial moments. I have this x coming out, so they correspond to moments in space of my measure. So in the end, this is just a calculation. In the end, what we get is that we are kind of interested in the correlation between the spatial variable x and the test function. And then the only thing we have to do in order to relate this to covariance is just to observe that if we look at this quantity, we can do Cauchy-Schwarz, and Cauchy-Schwarz is going to say that this quantity that controls the decay of variance is controlled by the variance itself of the function phi times the variance of x. Well, the variance of a linear thing is just has to do with the covariance matrix, and this is how the covariance matrix shows up. And yeah, I guess I'm out of time, but let me just mention that there's kind of a corresponding thing that you can do for entropy. And for entropy, the natural thing that comes up is very close to what Nima talked about in entropic independence. It's kind of like how the center of mass moves when you do a change of measure. And yeah, somehow these things, we've been able to apply them, for example, to get the first optimal mixing bound for the hardcore model for all degrees, and several other things. Maybe I'll just let you look at this slide that gives some applications of this.